pick up last week. We learned a bunch of stuff about finding derivatives. We learned some rules. So, some rule f plus g prime is f prime plus g prime. Derivative of the sum is the sum of the derivatives. We learned the product rule. Derivative of f times g is f prime g plus g prime f. We learned the power rule, which I guess it's going to come up again today. We didn't really show that it works for things other than integers, natural numbers, but you know, we may come across this. You can use it now as if you know for sure it's always true regardless of what n is. So the derivative of x to the n is nx to the n minus 1. Yeah. And in addition, we ran into derivative of e to the x. Exponential function is e to the x. I want to add something now, even though I can't justify it. We'll be able to justify it in a few days easily. But the derivative of a to the x, we know it's some constant times a to the x. We didn't figure out exactly what the constant is. I'm just going to tell you it's the natural log of a, the constant. And you can see immediately that e to the x fits this because the natural log of e is 1. So, you know, you can just remember this encompassing everything, but actually, keep this in the back of your head because it's going to come up a lot. Okay, so excuse me for a second. Anyone have any idea what that noise is?
He cut in the garage.
It's a weed whacker.
Yeah, the weed whacker, he cut in the garage.
It's amazing. My wife is, she's some kind of cat psychic. I mean, she's really good with cats. She socializes feral cats so they can get adopted. And we have 3 of our own. And she came up with this, this will make no sense, but that's all right. She came up with this toy online. It's a little plastic thing with a motor and a little thing that waves around and then a piece of cloth over it. So you turn it on and it starts going back and forth and the cats go crazy over it. It makes exactly that same damn noise.
It's two-stroke?
It's that same noise. Okay. I'll try and ignore it. Okay, so we're going to look, this is going to be section 3.2, and we're going to be adding to that list of derivatives, known derivatives, and rules and whatnot. And the rule we're going to add, the first rule we're going to add is the reciprocal rule. And the question is, what is 1 over the derivative, 1 over some function, the derivative of it, what is it in terms of the derivative of g? So, I guess spoilers here, we're going to find out it's negative g prime over g squared. So how do we get that? Well, we go back to our derivative definition. Limit as h approaches 0 of f of x plus h minus f of x over h. It's our definition of our limit, of our derivative. So how does that work here? Well, derivative of 1 over g will be the limit h approaches 0 of 1 over g of x plus h minus 1 over g of x. Well, we have to evaluate that a little. So we're going to do the thing you would, you'd probably do in 5th grade with a fraction. We're going to put it over a common denominator. So what do we get here? This is going to be g of x minus g of x plus h all over g of x plus h g of x. Oh, sorry, I left out the h. All right. That wasn't too quick what I did here. Just multiply this by g of x over g of x, and this by g of x plus h over g of x plus h. So that's my common denominator, and my h just stays there. All right, so now we're going to rewrite this as a product of, well, I'm gonna do a trick here. I'm gonna minus here, and a plus here, so I can switch these two. So g of x plus h minus g of x, put the minus outside because it's a constant, over h times 1 over g of x times g of x plus h. Well, the limit of a product is the product of the limits. And in particular, this limit we should recognize this right away, what this is. You want to do a little pattern matching here? What's the limit is h approaches 0 to the f? What's that?
Well, it's the one at the top there.
Hmm?
It's the same as the one at the top.
It's the same as the top, right? So this is the derivative of g. So minus derivative of g. These two, well, as h goes to 0, this just becomes g of x squared. So that's our reciprocal rule. I'm gonna kind of write it up here so we have a growing list.
That's what reciprocal rule. I think it's what reciprocal rule.
Okay. So that's another useful tool. Let's do an example. F of x equals 1 over square root of x. So g of x here is square root of x. So my rule tells me that derivative of f of x is what? It's going to be the derivative of the square root of x. Well, that's x to the 1/2, so the power rule tells me the derivative is 1/2 x to the minus 1/2, or 1 over 2 square root of x. So it's 1 over 2 square root of x over g of x squared, which is just x. So this becomes 1 over 2 square root of x cubed. So that's just, you could use the reciprocal rule that way. guess if we're feeling naive and we only know that the power rule goes from, or we could say from 0 on. 0? No, 1 on. And you say, well, wait a minute, can we use this somehow? Right. Say, well, let's make P of X equal to X to the minus N, or 1 over X to the N, where N is greater than 0. Let's just call it an integer for now. So, derivative of P of X is what? Well, our G of X here is X to the N. So that's, the numerator is easy. That's N X to the N minus 1. And below we have X squared, or X to the 2N. Okay? Oh, negative sign, I'm sorry. And I left out the negative sign here, sorry. All right, so now we just have to do some fiddling with the exponents here. 2n minus n minus 1 is what? It's just n minus 1. Is that what I want to do? No, I want to subtract 2n from n minus 1. So that's negative nx to the negative n minus 1. Okay, well, if I substitute here, I don't know, let's say m for negative n, you see that this just looks the same as the power rule. So the power rule, at the very least, works for all integers, except, work for 0? You don't need it for 0. 0 is a constant, derivative of a constant is 0. Okay, any questions about this?
I have a question.
Yes.
Well, this is kind of like an earlier problem, but when you were solving for the negative 1 over 2 square root x over x, how did you get negative 1 over 2x, or square root x to the cube?
This thing?
If that correlates to
Oh, no, no. How did they go from here to here?
Yeah.
Oh, okay. Well, the too short answer is exponents. But let me give you two ways to do this. Right? One way is 1 over 2 square root of x over square root of x squared. So this is 1 over 2 square root of x times square root of x squared is 1 over 2 square root of x cubed. That's one way to do it. If you didn't like that, that's okay. The other way to do it would be, this is 1 over 2 to the x to the 1/2. X is just x to the 1. So this is 1 over 2 x to the 1/2 plus 1, or 1 over 2 x to the 3/2. And x to the 3/2 and the square root of x cubed are the same thing. If you're weak, anybody's weak on laws of exponents, come down and see me, we'll go over all of it. I tried to cover this in the first day, but I know sometimes it takes a little to come back. Yes?
Well, the square root of x squared, why did you put that in there? How can you do that? Yeah, the first one. Yeah.
Well, it was x, right?
Oh, I see.
So isn't square root of x squared x. Yeah. Okay. And of course, I left out the minus sign again here, but don't forget the minus sign. All right.
The minus sign just comes from the reciprocal rule itself, right?
Well, okay, comes from the formula.
Yeah.
It came out of here because we had to switch, this was g of x minus g of x plus h. So to switch it, I put in a negative sign, so it's like this. That looks unclear. You can just remember the formula if you
Yeah, no, I'm just looking at the
want.
formula, the negatives in the formula.
Yeah. All right, so we have many formulas. You might be thinking, when will it all end? Two more important formulas. One of them we won't get to today. The next formula looks a lot like the reciprocal rule, called the quotient rule. And it answers the question, what is the derivative of f over g prime? Or what's the derivative of f over g? Gonna make some room here. Well, turns out we don't have to go back to the definition of the derivative, because this is just the derivative of f times 1 over g. And we can use the product rule, right? It says this is the derivative of f times the derivative times 1 over g plus the derivative of 1 over g times f. Well, we know the derivative of 1 over g. So what have we got here? We've got f prime times minus g over g of x. I guess I should put in x's here, plus, wait a minute, getting ahead of myself. F prime g of x plus negative g prime of x over g of x squared times f of x. Well, let's put this over. Wait a minute. I'm too stupid for my excellent notes here that explain this. Oh. That's my problem. Okay, so I put this over a common denominator, g of x squared. So what do we have to do? We have to say f prime of x, g of x. And I'm just going to put the minus sign in here. And this is g prime of x, f of x. All right, so that's the derivative of f over g, the quotient rule. Now, unlike the product rule, which is nice and symmetric and impossible to mess up, you can always like switch these two. It's easy. So how do you remember this? Well, you just have to kind of etch it into your brain that f prime g of x is the first term minus g prime f of x. Or that's what I try and do. You can, of course, put it on your cheat sheet for the exam, which I don't discourage. All right, so this is quotient rule. So, all right, how do you use this rule? Let's take an example, take a simple example. F of x equals 5x over x plus 1. So this is, I guess I already used f. Call this h. So f of x is 5x, g of x is x plus 1, and the derivative is what? It's the derivative of f of x times g of x minus the derivative of g of x times f of x over g of x squared. All right, so derivative of 5x, derivative of x is 1, so derivative of 5x is 5 times x plus 1. Derivative of x plus 1, well, derivative of 1 is 0, derivative of x is 1, so this is just 1 times 5x. And what do we have here? We have 5x plus 5 minus 5x over x plus 1 squared. So it's just 5 over 1 plus x squared. That's my derivative. So that's a simple example. I don't know why I feel like torturing you and myself, but that problem seemed too easy. Although, the only thing, I'll call it h again. The only thing really to be added here is how comfortable are you manipulating polynomials, since that's what these are. All right, let's try and do this a little more efficiently. So it's 6x squared minus 1, the derivative, that's f prime, times 4 times x to the 4th plus 5x plus 1, minus the derivative of x to the 4th plus 5x plus 1 times 6x squared minus 1, all over x to the 4th plus 5x plus 1 squared. Oh. Well, let's get to work here. This is 6x squared. Derivative is 12x. This is 0. X to the 4th plus 5x plus 1 minus, this is, derivative of this is, again, I'm just using the power rule here, 4x cubed plus 5 times 6x squared minus 1 over that guy. And I guess we can we can go a little further. 12x to the 5th plus 60x squared plus 12x minus, now I have to do FOIL here, so 24x to the 5th minus 4x cubed versus outer, inner, minus 5. You gotta watch where the minus sign is. Okay, so 12 minus 24 is minus 12x to the 5th. I left that out. Minus 4, oh, plus 4x cubed minus the minus. 60 minus 36 is plus 24x squared plus 12x plus 5 all over x to the 4th plus 5x plus 1 squared. Now, what an ugly beast. That's my derivative. But actually the problem I was really trying to solve is what's h prime of 0? That's pretty easy to figure out. 0, 0, 0, 0, 0, 5. I'll just write it. h is 0. And 0, 0, 1. So it's just 5. So that's the kind of problem you'd expect on the homework and maybe on an exam. All right. Reciprocal rule, quotient rule, every other rule we know can do an awful lot. And, just polynomials. I guess we could. Sorry? Oh.
Just asking if I wrote it down. I did.
Oh, I'm sorry. I'll erase this and wait. You can always look this stuff up, most of it, on in my notes on the website if you ever need to. Yes?
Are there certain times where you need to use specific rules, or is it kind of, if this rule fits better and it makes it clearer, use that one?
The latter. Okay, there often are, let's do an example here. I'm going to do a simple example. What's the derivative of 1 over x? Well, I can use the reciprocal rule. It's negative derivative of x, that's 1, over x squared. Okay, but if I use the power rule, it's just negative 1 times x to the negative 2, the same. It better turn out the same or math has a big problem, okay? Yes, any way you can simplify your work is a good thing, right? Because you make less mistakes. There might be a problem like, let's do derivative of x squared e to the x. Is there a way to do this without the product rule? It's not, I don't think we've learned anything if we do that. So this is x squared times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of x squared, is 2x. So this is just e to the x times x squared plus 2x. I don't know any other way to do it. Now, Thursday, we're going to cover something called the chain rule, which lets you break up a function by composition. And there are all sorts of ways you can use that. So that will probably give you more than one way to do one of these problems. And, use your best judgment, look for here's a good place to look for the easy way out. Just catching up here. We still have a comfortable number of people who are out sick. So, just a digression here. You guys all know, like, people who, like, in your dorms or something, who are out with, and it's, without trying to break any rules, it's like it's mostly COVID, isn't it? Yeah, okay. Well, hopefully in a week or two we'll be past all this. All right. So, the next section, we're going to add some useful derivatives, the trig functions, such as derivative of sine of x. And the question is, will I just write down the answer? That would be easy. But for some of you, that's probably the right thing to do. Just show it to you, so you have it when you need it. I'm going to kind of do a visual demonstration, but it's kind of tradition to show you a proof of this. The problem with this proof is at every level, every step is well within everybody's grasp, but it's kind of long and involved, and I'm not sure, I have my concerns about, I don't want to lose people over this. So, I don't know. Think of this as a journey back to high school in a way, because all of this is high school math until we get to limits. So with that in mind, all right, this is in the book, if you want to go back over it. When I'm done, it's section 3.3, and it's the derivative of the sine of x. Now, of course, what we're going to have to do here is we're going to have to say derivative of the sine of x is limit as h approaches 0, sine of x plus h minus sine of x all over h. I'm going to get a new tool here. And if you remember your trigonometry really well, you'll remember that we have a formula for sine of a plus b. It's going to be sine x cosine h plus cosine x sine h. And we still have minus sine of x over h. Limit is h approaches 0. Well, we have sine x here and a sine x here, so we're going to have sine x cosine of h minus 1 over h plus cosine of x sine h over h. And since sine of x and cosine of x don't have an h in them, we could rewrite this as sine of x limit as h approaches 0 of cosine h minus 1 over h plus limit as h. Take out cosine of x. Limit as h approaches 0 of sine h over h. All right. So we have these two limits here that we have to evaluate. And that's where the fun comes in. So let's first look at, see if I can do this in an organized manner. Let's look at the limit as h approaches 0 of sine of h I'm sorry, was that the one I did first? No. Cosine of h minus 1 over h. All right. To do this, we do a little geometry. We're going to draw a triangle with a hypotenuse of 1. Angle here, theta. And this is a sector with center over here. And from trigonometry, we know that the length of this side is sine of theta. Well, how do we know that? Well, opposite over the hypotenuse is the sine of theta, but the hypotenuse is 1, so the length here is sine of theta. And recalling that theta is in radians, the length here is just theta. Because theta times 1 is theta. Well, you can see here that sine of theta is always going to be less than theta, right? Because this sector is always going to be longer than the altitude. So let's write that as sine h is less than h. This is for small h. Right? But once your angle gets too far, things change. We're just looking here. So now, I guess I want to pause for a second and say, this is not a proof I would have come up on my own. This is kind of a traditional thing that gets passed on. Like I say, it's pretty straightforward, but again, it's kind of you have to follow each step carefully. All right, so since we know this is the case, I'm going to write something down. 1 minus cosine of h over h is, I guess we should make this equal because it's 0. These are equal. This is less than or equal to 1 minus cosine of h over sine of h. Okay, how did I get that? Well, sine of h is smaller. I divide something, 1 minus cosine of h, by something that's smaller, I get something bigger, right? If I have 5 and I divide 5 by 2 versus 4, if I divide by something, did I do this what I wanted to say? If I divide by something that's bigger, I get something that's smaller, right? So that's what I'm doing here. All right, now again, I do this thing you often find in proofs, you kind of pull a rabbit out of a hat, and we take this and we multiply it by 1 plus cosine of h over 1 plus cosine of h. This is always 1, so we can do that. And what do we get here? We get 1 minus cosine squared h over sine h times 1 plus cosine of h. And who can tell me the obvious simplification of 1 minus cosine squared h?
Sine squared h.
Sine squared h, that's right. It's the Pythagorean identity, sine squared plus cosine squared equals 1. All right, so we have sine squared h over sine h times 1 plus cosine of h. And for h not 0, this is just sine h over 1 plus cosine of h. All right, so now we have to go back to our problem here, which I wrote wrong. So, oh darn. I messed up a minus sign somehow. I guess it's not going to matter. I'm a little confused as to why the book is doing it this way, but they are. Okay, so we're back to trying to find out this limit here. So let's write down what we know. Limit as h approaches 0, 1 minus cosine of h over h, that's what we're looking for, has to be less than this. I'm talking about the limit here. Which is equal to limit as h approaches 0 of sine of h over 1 plus cosine of h. Now we want to evaluate this. Well, at h the sine is 0, but the cosine is, you remember which cosine of 0 is? You don't need to know this now, but you will, it's 1. So this is just 0. Okay. So now we know that this is 0. That's why the minus sign didn't matter. Minus 0 is just 0. Okay, so that's half half of what we wanted to show. Fortunately, that was the easy part. All right, now we want to find out what the limit h approaches 0 of sine of h over h is. Yeah.
Wait,
Yeah.
wait.
I'll write it back. I just want to squeeze it onto my board here. So this thing is 0 and sine of x times 0 is 0. So now all we're left with is cosine of x times this limit. That's, we're looking for our derivative. All right. As I said, this is a lot more involved, but again, we start with some geometry. Again, we have a triangle, hypotenuse 1, angle theta. The altitude here is sine theta. The adjacent side is cosine theta. And we have a sector here. We have a length here. We're going to extend this to here. And we're going to give these coordinates some names. It's probably a good time to take a break. Clear the mind. We'll come back and we'll finish this up. Before we start, are there any questions about anything so far? Okay. Again, keep in mind, this is kind of a neat proof we're going to finish up here, but it's not, again, it's the result that you're going to need, and it's going to be pretty straightforward. I thought to kind of enhance this a little, I go over two seemingly unrelated and facts. The first one is when we were doing limits at the very end of when we talked about limits, we mentioned something called the Squeeze Theorem. It says that if you have some C and near C, you have the following. F of x is less than or equal to h of x, which is less than or equal to g of x. So if for all x, when you're near C, this is true, and if the limit as f of x as x goes to c is equal to the limit as x goes to c of g of x. In other words, you're squeezing h between f and g. That equals some limit. Then you know that the limit as x approaches c of h of x is also equal to L. That's the Squeeze Theorem. Just a little reminder, because it's going to come in a minute. And then, reaching way, way back to those days when you learned geometry, you had this idea of similar triangles. So if I have try and draw these similar. What makes them similar? Well, they have two angles the same, so the third angle has to be the same. And if you know they're similar, you know something about the ratio of their sides. So for example, you can say A over B over AB over little ab is equal to AC over little ac equal to BC over little bc. In other words, the ratio of the sides is now equal. And you can rearrange these fractions as you wish. You could say AB over BC, little ab over little bc is the same as big AB over big BC. It's just a ratio. So something to keep in mind. All right. So, where are we? I guess I shouldn't make this a surprise. We're going to try and show that this is 1. And we're going to do it by squeezing it. But we have to set up that squeeze first. So, the first thing I want you to note here is we've got a right angle here and a right angle here, and we've got theta here. So that tells us that ABC is similar to, draw that very well, a little similarity sign, to ABD. Why is this triangle similar to this triangle? Well, they have a common angle, so that's equal, and they both have right angles, so they're similar. So we can set up a ratio here. We're going to set up BD. Let's see, I don't want to get this wrong here. BD over AB well, that's BD over 1, right? Because AB is just 1, just like the hypotenuse here. So that's going to be the same as sine of theta over cosine of theta. So I'm just making a ratio between this and this altitude and this length. Okay, so now I want to know what the area of triangle ABD is. That's the big triangle here. Well, it's going to be 1 times the altitude divided by 2. So 1/2, well, what did we decide the altitude BD is? That's sine of theta over cosine of theta. Next, so that's the first area we have here. That's going to be the largest area. The next area we want is this sector, ACB. Not the triangle, but the sector. So we have to think back, how does that work? Well, we have a unit circle, that's 2 pi, right? Well, actually, that's not what we really want to know. What we just want to know is the area of the circle. It's just pi r squared or pi. And the area of this sector, right, is going to be some percentage, right, of the entire area. So the area of the sector is going to be what? It's going to be theta times pi over 2 pi. It's going to be the ratio of this angle theta to 2 pi. Well, that's just equal to theta over 2. So we have this area now is greater than the area of the sector, which is theta over 2. And we need one more area here. What's the area of AC, whatever this is, we can call it E. Oh, I'm sorry, it's not this triangle, it's ACB, right? So again, we have the big triangle, we have the sector, and we have this triangle ACB, area of angle triangle ACB. Well, this is 1, its height is sine theta, so its area is 1/2 sine theta. And that, again, that's going to be less than this guy. All right, so we have 3 areas, and we know that this is the greater, this is in the middle, and this is less than. So now we're going to do some manipulation here. The first thing we're going to do, we're going to rewrite these inequalities, but we're going to multiply through by 2. So we have sine theta over cosine theta is greater than or equal to theta over 2. No, just multiply by 2, so it's greater than theta, which is greater than or equal to sine theta. Now, these are all positive numbers. So if I find their reciprocals, these inequalities are going to switch. I said like 3 is greater than 2. 1/3 is going to be less than 1/2, right? So let's do that. Cosine theta over sine theta is less than or equal to 1 over theta, less than or equal to 1 over sine theta. And then I'm going to multiply through by sine theta. So I get cosine theta less than or equal to sine theta over theta less than or equal to 1. Okay, so now I have this inequality that for small theta, as theta gets smaller, this is going to be true. So now I invoke the squeeze theorem. This is my two functions that this is always between. And let me find the limit as theta goes to 0. Right. Well, as cosine goes to 0, I'm sorry, theta goes to 0, what does cosine go to?
1.
Just 1. And what does 1 go to as theta goes to 0? Well, it goes to 1. So by the squeeze theorem, sine of theta over theta as theta goes to 0 goes to 1, or if you like, sine of h over h as h goes to 0 is 1. So all this boils down to derivative of sine of x is equal to sine of x times 0 plus cosine of x times 1. Cosine of x. Wow, all that work. I mean, it's a nice, pretty result, isn't it? It's like, oh, it's not some real complicated thing. Yes?
I just have a question about the two triangles being similar.
Yes.
So, since you changed B, how are they similar? Because they don't have two shared angles. Because there's not a 90 degree.
Wonderful question. I'm saying A, B, C. I'm sorry. Maybe I'm mentioning the wrong triangles here. I am mentioning the wrong triangles. Oh no, oh, I'm sorry. Oh my gosh. I messed something up. Give me a second here. I thought I was saying this triangle, AC whatever, and ADB are similar. They definitely are. Oh, well, maybe I missed a step here. We actually have three triangles in a sector here. This triangle clearly is less, the area is less, and that area is, we'll call it E. But then I snuck in this triangle here, didn't I? Well, this triangle, you would agree ACB has to be greater area than ACE, right?
Would we still be able to do this proof, or would this proof still work even if the triangles weren't similar, or do they need to be similar for it to work?
No. I think I left out a step here, but I got confused by it too. We have four objects here. We have triangle ADB, and I'm just going to you know, you say it's greater than sector ACB, which is greater than triangle ACB, which is greater than triangle ACE. That sound all right? So ADB well, we need to know its area, don't we? So BD is the tangent, actually. Is that right? I think that's where I messed up. This is the height. The tangent is the height dB. How do I know that? Because ACE and ADB are similar. I'll write that out. CE sine of theta over AE cosine of theta is equal to dB or BD over this length, which is 1. So that establishes, that establishes AB, area ADB is this. Have I got you confused?
Yeah.
Oh, all right. Let's see if I can, I think I actually had it the first time. You convinced me I had it wrong, but I might have said something wrong. All right. Let's think of triangle ADB. Right? We know ACE has sine theta and cosine theta. We know ADB is similar to this triangle. You would agree with that, right? So we know that side dB is sine theta over cosine theta by this ratio. Okay. So the area is 1/2 sine theta over cosine theta. That's the height times the base times a half. Nod your head when one way or another. No, I don't understand. Yes, I got it.
If everyone else gets it, we can just.
No, they're just sitting here like going, I wasn't paying attention. What's she talking about? But you're paying attention, so come on. You're the student who's going to come out of this really understanding it. So go for it. So you agree? ABD has area 1/2 sine theta over cosine theta. All right. The sector here, I don't know, were you convinced its area is theta over 2? And what's the last one? What's the area of ACB? It has a height of sine of theta, a base of 1, so its area is 1/2 sine of theta. Okay, so I just take this over there and manipulate it and come up with that. Yeah. Okay, thank you for. I like being put in my place. I did get it right. All right. Okay, any other questions here? Yes?
Why is the length of AB 1?
Why is it? Oh, well, this is a sector, right? That means its radius is 1.
Is that the only reason you put a sector up there, so you can get...
Maybe I didn't explain that. Would it be okay if I erase all this and just draw a better diagram?
Yeah, I've never come across like this before, actually.
Okay. So, let me try again. Picture, good picture is worth 1,000 words. All right. So, this is A, C, E. This is 1. And now, this is the center of the circle. So this is 1, and this is 1. I draw a perpendicular here, and I extend this to get D. And I call this B. Does that help?
Yes, and then the tangent, you said is, the tangent, sine or cosine.
Okay, so this is theta, this is 1, so this has to be sine theta, this has to be cosine theta. That triangle and that triangle are similar. They both have right angles and they share theta. So the ratio, sine theta over cosine theta, is equal to the ratio of, what did I call that? dB, dV, or BD, to 1. Because, you know, cosine theta, 1, sine theta, dB. So that means that BD equals sine theta over cosine theta. Of course, is the tangent. It brings up just a real minor thing I ran into just last year after all this time. Why do they call the tangent function the tangent function? A tangent is this, you know, idea we have a circle and a line intersects it here. Well, you can see the tangent to the circle here is this line. And I think that's where the idea of calling this the tangent comes from.
Does it give you a length then? Is BD I'll give you a measure of like a distance.
I'm sorry.
A tangent, is that like a distance?
Tangent is a trigonometric function equal to the sine over the cosine. They needed to give it a name, and someone came up with a diagram like this and said, well, this is the sine and this is the cosine, and you construct this. This particular line here is tangent at this point to the circle.
I was just wondering.
This is not an important point, but, you know, it's just, why are those two things, which seem to mean different things, given the same name? Trigonometric tangent, tangent to a curve, right? I never knew why they would use the same thing. This is the best explanation I've had. You could argue, well, so it's just the length. What does that have to do with being a tangent? I don't know. There's no. I think I have some stuff on my website that I might have described this there.
I got one more question. Actually.
Yeah. These are good questions, by the way. Yeah.
Law of science, can you use that in this at all? Where you find out.
So the law of sines says, let's go back. I guess I hope we don't need this anymore. The law of sines says if you have a triangle, alpha, beta, gamma, I don't know if these here, that the ratio of, say, A to the sine of theta is equal to the ratio of, I guess I should say B. I guess I used the wrong Greek letters, but B to the sine of alpha is C to the sine of gamma. Now, we're dealing, which triangles do you want to look at? I mean, the right, so we look at the right triangles, right? So, this is theta, sine theta, cosine theta, sine theta over cosine theta. And I'm kind of drawing a sector. So where does the well, it might have something to do with it, but I don't see it right offhand. Now you've given me homework. That's fair. Give you guys homework all the time. All right. All right, so let's kind of complete the thought here. We are gonna do a couple hand waves here. Well, no, before I do that, we established derivative of sine of x is cosine of x, but I really think that needs a little feel to it. I can't bring up, I forgot my keys, so I can't bring up Desmos, but I think I can draw a credible diagram here. So first I'm gonna try and draw a decent sine curve. Okay. And so I use some orange, which you never can use. So the cosine, of course, is just this function phase shifted. So all right, let's see if we can notice something about this that makes sense. This point, 0, sine of 0 equals 0. But here, think of it, this is the peak of the cosine. Cosine of 0 is 1. So our formula says the derivative of the sine at 0 is the cosine of 0, which is 1, which is exactly right. Did I say that right? No. I guess it's not obviously exactly right. If you think about this curve as it reaches its limit here, right? As we go further, it gets less. Here it gets goes back to 0. So it reaches a peak here at 0, which is 1, which is what the cosine of 0 is, 1. As we get up here to pi over 2, sine of pi over 2 is 1, right? But what's its derivative? It's obviously 0. And what's the cosine of pi over 2? It's 0. So what I want you to kind of get a feel for is that, I have this function, I have this formula over here that says that the derivative of the sine is the cosine. But in fact, right at 0, its tangent is about 1, is what the cosine is. So you move on up, it gets less and less, the cosine gets less and less, and exactly where the sine peaks, and you have a horizontal tangent, slope 0, that's exactly where the cosine hits 0. And, you know, if you follow this through, you'll find the same thing happens. Here we have a slope of -1, and the tangent has value -1. And here again, the sine will go to 0, exactly where the cosine is. The tangent will go to 0 where the cosine is 0. So, I don't know if that helps kind of understand this a little better. That is to say, our algebra seems to comport with what we visually see here, which is always a good sign. All right. It would be an act of wanton abuse for me to want to go, at me and you, for us to go through all this again for all the other trig functions. So we won't. We'll just kind of write down the derivative of the cosine of x is, you were hoping it was going to be the sine of x, right? But it's not. It's the negative sine of x. That's okay. Let's see. This has to be -1, right here. This angle here, where the cosine crosses, you know, pi over 2. Well, this is 1, not -1. So you can kind of see the negative. It's just a kind of a phase shift thing. Where the cosine is 0, well, yeah, it's 0. Sine is 0. So, I guess back here, where the cosine is negative pi over 2, the slope of the cosine is going to be 1. But what's the sine of negative pi over 2? It's going to be -1. So, now, while it would be awful to go through a, you know, proof from the definition of the other functions, we don't have to. We can just use our newly found quotient rule. So if we want to find the derivative of the tangent, that's the sine over the cosine. So it's going to be the derivative of the sine times the cosine minus the derivative of the cosine times the sine over the cosine squared. That's the derivative of the tangent. Okay, we need to do a little work here. Derivative of the sine is the cosine. So we have cosine squared x minus the derivative of the cosine is the negative sine. So that's going to make this a plus sine squared x over cosine squared x. But of course, sine squared plus, so cosine squared is 1. So it's cosine squared x, which we write as the secant squared of x. This is a useful piece of information to put to memory. Derivative of the tangent x is secant squared of x. I'm going to You can repeat this, this doesn't come up as often. The cotangent, derivative of the cotangent of x, that's just 1 over the tangent. It'll come out similar. It'll be the cosecant squared of x, but once again, you get a minus sign introduced. And that leaves us with, what is the derivative of the, let's do the secant of x. Well, that's 1 over the cosine of x. So we can use the reciprocal rule. So that's negative derivative of the cosine of x, which is the sine of x, over cosine squared of x, which we usually write this way. We say that's the sine of x over the cosine of x times 1 over the cosine of x. So it's the tangent of x times the secant of x. This is, they're both valid, but this is the way we usually write it. So, derivative of the secant of x is tangent times the secant. And again, I'm going to skip, you can repeat what I just did. Derivative of the cosecant is going to be negative cotangent of x times the cosecant of x. So there's some nice patterns here. Again, you better know the derivative of the sine and the cosine in your head. That's so important. The other ones you can kind of jot down on your cheat sheet, bring it in, in case it comes up and you happen to forget. I'm going to point out a nice little feature of the first two derivatives. We have the derivative of the sine of x is the cosine of x. But the second derivative of the sine of x is the derivative of the cosine, which is the negative sine of x. The third derivative is going to be negative derivative of the sine of x, or negative cosine of x. And finally, the fourth derivative is going to be the sine of x again. So you have kind of a cycle here. Okay? You can find further derivatives, but you can find them in this list here. Obviously, the same as the cosine of x. After you find its derivative 4 times, you're back where you started from. That's not true of the other functions. One way to look at this is just how you start with a sine function, and you phase shift it pi over 2. Well, if you do that 4 times, you come back. It's a periodic function. So that's another way to think of it. They just find this stuff is really, this is really pretty, and the only thing prettier than this, we're gonna have a section in a few days on something called a hyperbolic function. These are circular functions. Remember, we've got points on a circle. Hyperbolic functions are kind of similar, except they're not periodic. They're points on a hyperbola, and you're going to see similar pattern and similar relationships here. Just really pretty, beautiful symmetries you sometimes get in mathematics. these otherwise mundane but useful functions. All right. I think that's really all for today. I'm going to, if anybody came in late and didn't get their homework back, come see me. I may release an assignment today, but it won't be due until next Tuesday, and then another one on Thursday, which will be due on Saturday. Talia,